This lesson's about compound interest, and we're going to review it a little bit, and then we're going to expand a little bit past what we've already learned. We're also going to learn about Euler's number in the process. So let's just quickly talk about compound interest. So if you deposit money into a savings account in a bank, often you will earn interest, and that's called compound interest. And the formula that they use to calculate compound interest, this is one of them, which you should have seen before, is A equals P times the quantity 1 plus R raised to the T. A is your final amount, what you end up with, your balance at the end of whatever amount of time has passed. P is called the principal, which is what you start with, the money you deposit in. R is the rate. It's given to you generally as a percent, but you have to convert that percent to a decimal. So, for example, 3% has to be written as 0.03. And then T is just time, so if it was a bank, it would be the number of years. Now, this formula also can be used for non-bank scenarios where you have a percent change that is being compounded. The same percent change happens over and over again. Some examples are population growth generally follows this, or radioactive decay can be modeled this way. Now there's a second compound interest formula which only works for banks, and that is if the bank chooses to compound the interest more often than once a year. And that's not uncommon, actually, quite common. So N is the number of times the bank is going to compound your interest in a year. However, they still report the rate as a per year rate. So they'll say 3% APR, for example, annual percentage rate, but then they'll compound it, I don't know, let's say monthly. So if they're compounding monthly, well, you're not going to get that entire 3% in that 1 month. You will get a 1/12 of that 3% because only 1/12 of the year has gone by. So you take the rate and you divide it by the number of compounding. So with the example I just described, you divide by 12. But then you would perform that calculation 12 times in 1 year. So that N there up here is how many times you have to perform that calculation in a given year. And then, of course, you multiply by the number of years to figure out how many total compounding calculations you did. So this formula is for compounded N times a year, whereas this formula is for compounded annually. So these two formulas should be in your notes. You probably have already learned them, but anyway, put them in your notes. But I'm now going to do an example where I mess with one of these formulas to try to come up with a new concept. But I don't want you to take notes on that. Just follow along the next slide, and I'll let you know at what point you should start taking notes again. So now we're going to take this concept of compounding multiple times in a year a little bit further. So we're going to create a sort of an artificial scenario just to keep the numbers simple. We're going to deposit $1 in the bank. The bank's going to offer 100% annual interest for 1 year, and we're going to compare the different number of compoundings to figure out what the balance is. So this is the formula we need to use. A equals P times 1 plus R over N to the NT. The principal is $1, so 1. The rate is 100%, so R equals 1. When you convert 100% to a decimal, it's just 1. And then T is 1 because it's 1 year. What is going to change, though, is the number of compounding, so N. So this is the formula we're using, and we're going to plug in different values for N. So the first is going to be, we're going to compound annually. That's the least complicated, so N is 1. So this is now 1 plus 1 over 1 to the 1. Well, that's just 2, which makes total sense. If you're getting 100% interest, that means you should double your money after 1 year, assuming it's only compounded once in a year. So now we're going to compound semi-annually, which means twice in 1 year, because it takes half a year before you compound. So the formula now looks like this, because N is 2. And as expected, yes, you're getting a smaller rate for that 6 months, but because after 6 months you now have extra money, the next time the calculation gets done, you end up getting additional interest, so you end up with $2.25, which makes sense. The more often you compound, the more money you should have in your bank at the end of the year. So now we compounded quarterly, which means every quarter of a year, so 4 times in 1 year, so N is 4, and this is the formula, and then using the calculator, this is what we get. Now, it has gone up. It went from $2 to $2.25, then it went from $2.25 to $2.44 and some extra stuff, which I'm going to keep all the decimals for this example. So it has gone up. You compounded more often, you made more money. So now we compounded monthly. In other words, n equals 12 because you do the compounding 12 times. So here's the formula. Divide the rate by 12 and then do the calculation 12 times and you end up with this amount of money, which is a pretty big increase from the $2.44. Now you have $2.61 and some extra decimals. So now I'm going to create a second slide of this to keep this pattern going. I'm going to erase the 1, 2, 3, and 4, and I'm going to restart this slide. So here are the final values that I had for compounded once a year. I got $2. Compounded twice a year, I got $2.25. Compounded 4 times a year, I got this number. Compounded 12 times a year, I got this number. So now I'm going to keep this going. So now I've decided to compound daily. The previous one was monthly, so let's go with daily. There's 365 days in a year, let's just say. So the final balance is 1 plus 1 over 365 raised to 365, and you get this number, $2.71 and some extra decimals. All right, so it went from 2 to 225 to 244 to 261. It keeps getting bigger. How much bigger can it get? So let's try it again. So now I'm going to compound every minute. There happen to be 525,600 minutes in 1 year. So when I plug that into the formula, I end up with this amount of money at the end of the year. Well, that is an increase from the daily, but not by much. The 2.71, those first 3 digits are exactly the same. It's that 4th digit that changed, but it is bigger. 2.714 versus 2.718. I'll grant you that it has gotten bigger. Let's keep this going a little bit further. So this time I've decided to compound every second. It turns out there are 31,536,000 seconds in a typical year, or in a regular 365-day year. So I plugged that in and I got this number. Well, it is slightly bigger than the every minute, 2.718279, 2.718281. So that 7 has turned into an 8. That's like the 1, 2, 3, 4, 5, 6th digit in where there is an increase. The first 5 digits now are fixed. They're not changing. So there is an increase, but it's just really slowing down. It's very much like an asymptote. Well, what is this value getting closer to? Well, that is the number called e. So what we've done is called a limit. As you made n bigger and bigger and bigger, that's a limit. N was trying to get to infinity. Of course, infinity is not an actual number, so we just increased it as far as we could until we figured out what the pattern was, and we noticed that the values kept getting bigger, but then the increase slowed down quite dramatically. So if you were able to do this for very, very, very large numbers of n, you would end up with something like this, 2.71828182845945, and it actually keeps going, and we call that number e, the lowercase e. Now, Leonhard Euler is the mathematician who figured this out, and the story goes he did not actually name it after himself. It's not e because of his name E. It just happened to be the next letter in the alphabet after the variables he already kind of figured were taken. So anyway, neither here nor there. The number E is approximately this. It is irrational. In other words, it cannot be written as a fraction, just like pi is irrational. In fact, E is just as, if not more, important than pi. I wanted to point something out here, that the calculator actually had some trouble with this value and this value. It started rounding way too early. So past the 365 times in a year, in other words, the daily, I had to use a computer to make sure that I got the decimals to work out correctly. But that's just an aside, a little story. So now you should start taking notes again. So we've discovered that e, the number e, which we've defined, is the limit as n approaches infinity of 1 plus 1 over n to the n. And this is the first, I don't know how many ever decimal values of it, 2.718, etc., etc., etc. It is an irrational number, so it can't be written as a fraction using integers, just like pi can't be written as a fraction using integers. And if you remember with pi, most people just remember pi as approximately 3.14. It's good for just sort of getting a general sense, is pi bigger than 3? Is pi bigger than smaller than 3.2? Just getting a general sense of where pi is compared to other numbers. So the same thing is true with e, except that it's probably okay if you just remember 2.7. That's all I really expect you to remember. The more you want to memorize, the better, but 2.7 is an acceptable limit. Of course, you cannot use 2.7 for e. You need to use the number e. Now, luckily, e is on the calculator. It's actually on there twice. That's how important it is. But I'm going to show you just one of them. So on the TI-84 Plus calculator, you hit the second button, and then right above the division symbol, it should say blue E. And so second E will give you, or second division will give you the E. And if you hit enter, you should get some of these decimals. The calculator doesn't go quite this far. But anyway, you should be using that button if you need to calculate using E. But if you want to make a comparison of, how big is E compared to other numbers, 2.7 is a good approximation. But now we have a new compound interest formula. So these are the two that we had before. Compound interest formulas were non-bank examples, or compounded annually, a equals p times 1 plus r raised to the t. Compounded n times a year, a equals p times 1 plus r over n raised to the nt. And now we have this idea of compounded continuously. And that just means we let n approach infinity. In other words, we're infinitely many times we're going to do this compounding. And of course, you can't actually do infinitely many times, but it turns out that this formula will accomplish that goal. P is still the principal. E is now the number E, Euler's number. So 2.7 whatever, which you're going to use the calculator, of course. And then R is your rate. So again, if it says 4%, you do 0.04. And then T is the time. So if it's 3 years, you do 3. So this is the new compounded continuously formula. So let's do an example of compounded continuously. So Laura deposits $5,000 in a bank that offers 6% APR compounded continuously. Find the balance in her account after 3 years. So the formula, because this is compound continuously, A equals PE to the RT. Now the numbers I know right now are, well, she deposited 5,000, so that's the P, 5,000. And then E is just the number E. And then it said 6%, so I need to convert that to a decimal, 0.06. And T is the number of years. It says 3 years, so 3. And now I plug this in my calculator. And because it's money, I'm going to round to the nearest penny, or the nearest 100th of a dollar. So we get $5,986.09. Now on the calculator, you would have typed the 5,000, and then you do second and then e to the x to get you into e raised to some number, and that e to the x is on the left-hand side above the button that says ln, and then you can use parentheses 0.06 times 3. If you're using the old operating system, you have to have the parentheses. With the new operating system, it'll already have the exponent. Now you could also use the regular old e button and then use an exponent after that to accomplish the same thing, but e to the x is going to be quicker for you. So now we have another problem. Muhingo deposits his $5,000 in a bank offering 6.15% APR compounded annually. Will he get a better return than Laura after 3 years? Well, first of all, he's got a better interest rate. 6% was Laura's interest rate. He's getting 6.15%, so that's an advantage. However, compounding continuously is an advantage over compounding annually. So how much of an advantage? Is 6.15 enough to beat out the 6% because it's been compounded annually? Or is the compounded continuously going to be enough to beat out the compounded annually because the 6 is close to 6.15? So let's figure this out. Now this is, of course, a different formula. Compounded annually, so it's A equals P 1 plus R to the T now. And of course, the principal was 5,000. 1 plus. Now the rate here is 6.15%, so 0.0615. And the time here is 3, so raised to the third. And you plug that in your calculator, and again, round to the nearest penny. And I get 5,980.40 when I round it. So 5,986 and 9 cents is better than 5,980 and 40 cents. So the question is will he get a better return? He will not get a better return. Now, here's another thing to keep in mind, that once it's decided that Muhingo is getting a worse return than Laura, he has less money in the bank. And so even if he continues to do this compounding, there's never going to be a chance for him to catch up, because Laura is going to keep having more and more and more money in her bank account. So you didn't actually have to go to the 3 years. You could have just waited for 1 year to pass by to figure out who had more money after 1 year, and then whoever was winning after 1 year was going to continue to win moving forward. So now let's do some practice using the number e. So if it just says simplify and it doesn't say evaluate or give me a decimal, you can treat e just like it was a variable. It's really not going to do anything different. Just like you could treat pi as if it was a variable, even though we know it's not a variable, it's a number, but you can treat it that way. So if I want to simplify this, the first thing I need to do is I need to distribute that exponent of 3. So I'm going to have 5e squared times 2 cubed, and then e to the 4 times 3, which is 12. Of course, 2 cubed is 8. So now I can put the 5 times the 8 and get 40. And then to do e squared times e to the 12th, I add the exponents to get e to the 14th. And it's simplified, and it says using only positive exponents. That's a positive exponent. So that's as far as we can go. It did not say get a decimal. It did not say evaluate. This is all we need to do. So let's look at the next one. So we have 5e to the x plus 1 quantity squared times e to the negative 3x minus 2 over 10. Again, we're going to treat e as if it was a variable, just like x is here a variable. So first thing I want to do is I want to deal with that exponent around this parentheses over here. So since it's all one term, I can distribute that square. So I have 5 squared, and then e to the, well, I have an exponent x plus 1, and then I have that exponent 2 in the parentheses. Those have to get multiplied, but 2 has to multiply by all of x plus 1, so it distributes to get 2x plus 2. And then times e to the negative 3x minus 2, and then over 10. Now, because I've got a fraction on the right, I'm going to make the left one also a fraction by dividing by 1. Okay, so now I've got 5 squared, which is going to be 25, and then I have e to this and then e to that, and then over 10. Well, I want to put these two expressions together with that base e by adding the exponents together. So first of all, I'm going to write 5 squared as 25, and then e to the, well, let's see, I want to add 2x plus 2 plus negative 3x minus 2. Well, that's just going to be negative x, and then, of course, over 10. Now the 25 tenths will simplify because both of them are multiples of 5, so I can call that 5 halves. So let me move over here. 5e to the negative x over 2. But there's one more problem, which is it said using only positive exponents, that's a negative exponent. Well, e is being raised to the negative x, so e is in the wrong half of the fraction. E needs to go in the denominator, and x will turn positive, that exponent. So 5 over 2 e to the x is the simplified version of this using only positive exponents. So now let's graph functions involving e. Well, first of all, remember e is about 2.7, so he's bigger than 1. So this should look like exponential growth. Now, when you get to calculus, this is going to be your favorite function ever. It is very, very convenient, but I'm not going to worry about that right now. Anyway, so let's figure out what e to the x looks like. Well, I'm just going to start with a table because I have no idea. And I'm going to pick convenient numbers for x, so negative 2, negative 1, 0, 1, and 2. And then I'm going to plug them into the calculator. Well, e to the 0 I know is just 1, and e to the 1 is just e. And for purposes of graphing, 2.7 is pretty close to as detailed as I could possibly get. So I'm going to go with 2.7. And then I'm going to plug all the others into the calculator. So I plugged e to the negative 2 in the calculator. I got this, and it kept on going. But again, I can't be that precise on the graph, so I just called it 0.1. I rounded to 0.1. And then e to the negative 1, I got something like this with some more decimals after that. And again, I can't be that precise, so I just called it 0.4 because I rounded that. And then, of course, I did e squared, which was about 7.389, et cetera, et cetera, et cetera. But again, I can't be that precise, so 7.4. So I'm going to use these 4 values with the x values over here. So now I'm ready to graph. So I'm going to put the points on there approximately. So -2 and about 0.1 is maybe there. And then -1 and about 0.4 is maybe there. And then 0, 1 is maybe there. And then 1, 2.7 is maybe there. And I actually can't fit the 2, 7.4. So I'm going to go with this. And the graph looks something like that. And then don't forget the arrow. And once again, you get exponential growth like we expected. And you get a horizontal asymptote here on the x-axis. So now the question says domain and range. So let's talk about the domain. Well, like with all exponentials, the input values, the x, can be anything, and it's all connected, so real numbers. And the range, once again, like any exponential growth function, there is a low end. The graph tries real hard to get to y equals 0, but can't quite make it, and it goes up from there. So y is an element of the reals such that y is greater than 0. Okay, for this one, I want to notice that the graph got moved down 3 because I'm subtracting 3. This 2 is part of the coefficient, so I'm not going to, it's not part of adding or subtracting. This is down 3, and then I've got this negative x. So again, you can do this as a reflection across the y-axis, or you can treat this differently, and I'm going to do it the second way. So I'm going to say, really, g of x equals -3 plus 2, and then times 1 over e to the x, because the negative x means I have to take a reciprocal of just the e, because it's only applying to the e, so 1 over e to the x. And of course, if e is 2.7 approximately, then 1 over e is between 0 and 1. So I expect exponential decay from this, not exponential growth the way it was sort of implied over here, but if I had ignored the negative x. So this is exponential decay, but the graph did get moved down 3. And the 2 out front is not attached to x, so it's changing y. It's going to be a vertical stretch by a factor of 2, which means y is going to become 2y. So now the parent, after all that, well, y equals, and I'm using this version, so 1 over e to the x. Now I make my table for the parent function, and you're going to need to rely on the calculator, -2, -1, 0, 1, 2. When I plug in x equals -2, I get approximately 7.4. When I plug in x equals -1, I get approximately 2.7. When I plug in 0, I get 1. When I plug in 1, I get approximately 0.4. And when I plug in 2, I get approximately 0.1. Again, 1 decimal place is the best you're going to be able to get here. Now I need to put in my new y because of the vertical stretch. So new y, well, I double all those. So let's say 14.8 and 5.6 and 2 and 0.8 and 0.2. Again, these are all approximations, so don't stress too much over it. Now I'm ready to graph this. So the first thing I do is I go down 3 and I draw my open circle. I draw my fake x-axis. The y-axis did not move. And of course, the fake x-axis is now going to be the horizontal asymptote, so it's very important to have that dotted line so everybody can see where the asymptote is. And then I start plotting the points, pretending that's the origin. So now I can't fit the -2, 14.8 on there, but I can fit the -1, 5.6 on there. It's about there. And then the 0, 2 is about there. And then the 1, 0.8 is about there. And the 2, 0.2 is about there. And you can see this exponential decay, like we had said. It's going to look something like that. And now I need to find the domain and the range. So the domain, once again, all real numbers. And the range, well, y is an element of the reals such that the y gets closer to -3, but doesn't quite make it because of the asymptote, and then it's above, so y greater than -3. All right, final example. We have y equals -1/2 e to the x minus 3 plus 4. First I notice is it moved right 3 and up 4. Now I also notice that there's a negative in front of everything and there's a 1/2 in front of everything. It's not attached to x, it's going to change y, so the negative makes it reflect across the x-axis, and the 1/2 makes a vertical shrink by a factor of 1/2. If I put those two things together, y is going to change to negative 1/2 y. And other than that, the parent now is y equals e to the x. So I'm going to make my table. And again, I plug numbers into the calculator. And again, I regenerated my list. And then I need a new y. And I need to multiply by negative 1/2, so negative 0.05, negative 0.2, negative 0.5, approximately negative 1.35, and then about negative 3.7, give or take. And now I'm ready to graph this. So again, I move right 3 and up 4. That puts me right there. I draw my fake y-axis and my fake x-axis, and of course the fake x-axis is kind of important because it becomes the asymptote. And then I plot the points pretending I've got my origin, and I end up with points -2, negative 0.5 is 0.05 rather. It's really close to the asymptote there. -1, negative 0.2 is maybe over there, and then 0, negative 0.5 is maybe over there. And then 1, negative 1.35 is maybe somewhere over here. And then 2, negative 3.7 is maybe somewhere over here. And I've got my general shape. And again, you can see that asymptote on the left-hand side. And you need to make sure you draw an arrow so it's really obvious. So you see the reflection across the x-axis, so it's an upside down. It was an exponential growth to start with, but it got flipped over the x-axis, so it starts to fall, but it falls very fast. And I need to now do the domain of the range. So the domain, well, that's all real numbers. And the range, well, the highest that y gets almost is 4, doesn't quite make it. So y is an element of the real numbers such that y is less than 4. And that is the end of the lesson.